Hello. In this video, I'm going to introduce the idea of a line of best fit. We will at later points be using technology to find lines of best fit, but for this video, just the basic idea. So the table below here, it's giving the frequency of chirps by grasshoppers at different temperatures. So oftentimes when we gather data like this, we ask ourselves, is there a relationship between temperature and the chirps per minute of these grasshoppers? And one of the things that can help us to sort of assess if there's a relationship or not is by graphing this data on the scatter plot. So that's what I have here is a scatter plot. Now, when we look at the arrangement of these points, it's obviously not a perfect line, but we can see a bit of a linear trend. And when we can see a bit of a linear trend, so we see this right here, that sort of gives us a hint that there's maybe a line on there. So this, I mean, I've drawn one possible version of a line of best fit just as by eyeballing it. But we have, slightly better techniques. For one thing, I would probably use a straight edge, so a ruler or something like that. On my computer screen, that's a little trickier to put a ruler on, but I do actually have an advantage here in that I can use a drawing tool to draw a perfectly straight line. So there's one possibility. Now, one thing on the computer that's kind of nice is I can now sort of mess around with that a little bit and see, like, is there movement? I can move it a little bit. Obviously, that's not as good a fit. I'm trying to sort of get it as much as possible centered in those points. It doesn't necessarily have to go through any of them, although where I have it drawn now does actually go through a point, and it's pretty close to a bunch of others. So this could be considered a line of best fit, and then we could go about finding the equation of that line by using points on it. This isn't a perfect grid, so it's not entirely, I guess, accurate in terms of being able to tell exactly what the coordinates are. But this point right here is pretty close to being able to estimate that that is the point 70, 35. And then this point down here is on the line, so I could, that's the point that is the lowest temperature, so 52.19. That's this point right here. So with those 2 points, I could find an equation for this line of best fit. I could say, well, the slope is delta y over delta x. In this case, what I've drawn, 19 to 35, is an increase of 16. That's delta y. And 52 to 70 is an increase of 18, so that's delta x. So if I simplify that, I end up with 8 over 9 as my slope. That's an estimate, obviously, of what the slope I think could describe this is. And if I drew a slightly different line, I would have a different equation. So if I were drawing this on paper with a ruler, I would expect that different people would have slightly different equations, but they should all be sort of in the same ballpark if I put them to decimals. So now from there, I say, well, okay, let's find the equation of a line. I'll use the point 52.19. So y minus 19 equals the 8/9 times x minus 52, which means that y equals 8 over 9x. Now this is the part that's a little bit, it's going to be kind of an ugly fraction, but I have 8/9 times 52, which is negative. And then I'm going to add 19 to that. So I get about negative, I'm going to actually put this as a decimal, negative 27.2. And I'll round it. So I'm actually going to put the slope as a decimal too. I'll call that 0.89, a rounded value. There's no point in putting the repeater, the 0.8 repeating, because that's very precise, but this is all just an estimate anyway. So this equation could be considered a best fit line here. An estimate. I can check if I were to substitute in to this equation the other point, the 70/35. So using the rounded values, if I take 0.89 times 70, and to that I subtract 27.2, I get 35.1. So pretty close to where that point is. And I could then use this equation to estimate other values, other chirps per minute. If I say, well, okay, what about if the temperature was 60? Notice I didn't have any data in my table for where the temperature was exactly 60 degrees Fahrenheit. But if I say, okay, well, what if now the temperature, which in this case I've represented with X, was 60 degrees Fahrenheit, what would I expect to get for the number of chirps per minute? And for that, I would simply plug it into this equation. So 0.89 times 60 minus 27.2 actually gives us 26.2. I'm going to just call that y equals 26, partly because it's only an estimate anyway. So 26.2 makes it seem unnecessarily precise, but also because chirps per minute probably should be a whole number. So 26 chirps roughly per minute is what I would expect at 60. And if I look at the graph at 60 degrees, so right here, that is pretty close to where we are. So that's how I could use a line of best fit. There are some mathematical techniques that we use to kind of make it as accurate as possible, and we will explore those at a later point.